Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Raluca Arapopa. So Raluca is a student, a PhD student at MIT, and she's done a lot of great work in security and cryptography, and in particular in issues related to privacy in the context of cloud storage. And today she'll be talking about some of her work on encrypted databases.
Thank you, Sani. Thank you, everyone. Can you hear me well? Is the mic working? Is the mic working? Maybe I'll put it. Is it better now? Yes. Okay. So I'll tell you about CryptDB, which is a system for protecting the data in a database by computing unencrypted data. This is joint work with Catherine Redfield, Nikolai Zeldovich, and Hari Balakrishnan from MIT. So we hear many times in the news that confidential data leaks from databases. To give you a few examples, the Homeland Security Newswire listed that between 2009 and 2011, 8 million medical records were leaked. Also, another example is last year, a group of hackers infiltrated into the Sony PlayStation network and were able to access 77 million user profiles, many of which contain credit card information. So there are many reasons why confidential data leaks. And here in this talk, we're going to consider attacks to the database server. So for example, hackers notoriously break into database systems and steal sensitive information. Or in fact, system administrators oftentimes have root access to the database servers and may be able to read company data such as financial or medical, when really their only task is to maintain the database servers. So we group all these attacks together into one threat that we call passive database server attacks. So basically, the database server can be attacked, an adversary can have full access to the database server, but it's passive, meaning that the attacker doesn't actually change the data or issues queries. It just tries to read confidential information. Yes?
If you add database administrators, they have legitimate reasons to change the database on top of it.
Right. So here, okay. So for example, if you look at system administrators that only have to balance the load, they don't necessarily need to look at the data, but oftentimes they actually can. So that's one threat model. And just to, for cryptographers here, by passive we mean honest but curious adversary. Okay. So the approach of CryptDB is to process SQL queries on encrypted data. And the reason why we take this approach is that in this way, the database server never gets the decryption key. It only gets encrypted data. So even if an attacker gets full access to the database server, the attacker still cannot learn anything other than encrypted data. So before I explain how CryptDB works, let me summarize at the high level CryptDB's contributions. So CryptDB is the first practical DBMS to process most SQL queries on encrypted data. And really in CryptDB, we focused a lot on practicality. One can use CryptDB, for example, to hide the database from system administrators while still allowing them to maintain the database servers. Or it can be used to put a database on the cloud. One of the main contributions of CryptDB is that it has a modest overhead. So CryptDB has a 26% throughput loss for TPC-C as compared to MySQL with no encryption. So by throughput, what I mean is the number of queries per second that the server can execute. And TPC-C is a standard industry database benchmark. And perhaps surprisingly, CryptDB makes no changes to existing DBMSs, such as Postgres and MySQL. And I will explain later why. And also, it makes no changes to existing applications. So basically, applications can run on top of CryptDB without knowing that they're actually running on top of CryptDB. And that's because CryptDB exports SQL interface. Okay. So to explain the approach of CryptDB, let me put it in relation to existing approaches. There are really 2 points in the design, 2 extremes in the design space in terms of practicality and security. So at one extreme, there are unencrypted databases. So these are very efficient. They've been optimized for over 40 years of experience. And they're efficient because they process simple operations such as equality. How many items are equal to 100, for example, in a column. And also because they have specialized data structures such as indexes. So you can think of an index as a search tree that helps the database server locate items fast. At the other extreme, there's fully homomorphic encryption, which was first constructed by Craig Gentry in 2009. So shortly, it's called FHE. So FHE allows any kind of general computations to be performed on the data, and it has great security, semantic security, which virtually leaks nothing about the data. However, it is prohibitively inefficient. Yes, there have been a lot of improvements in practicality of FHE since then. For example, Gentry, Halevi, and Smart in 2012, they implemented AES on top of FHE, and they did some clever optimizations. However, even then, the scheme was 9 orders of magnitude slower than unencrypted computation. And in fact, even besides the cryptographic overhead, there is one main inherent reason why FHE is impractical for databases. And here is the reason. So in order to compute a query on a database, the client has to express the query as a circuit over the entire database, which means that for every single query, the entire database has to be processed. Whereas in a real database, the database server just uses an index and allocates items fast. So our idea with CryptDB is to try to come at an intermediate point. Ideally, we'd like to be almost as fast as unencrypted databases, while at the same time having a high degree of security. So the insight into the practicality of CryptDB is to try to have the computation on encrypted data be the same as on unencrypted data. So for example, if we do an equality check on unencrypted data, that should turn into an equality check on encrypted data. And also indexes should still be useful. And the insight here is that, in fact, most SQL operations use a limited set of operators. So if we can support those with efficient encryption schemes, then we are roughly mostly done. In terms of the security that that achieves is, well, we will reveal the server relations necessary to compute a query, but really no relations among the data beyond those needed to process the query. And I will go back to explain the security in more detail. I would like to mention other related work. For example, search on encrypted data, initially pioneered by Song et al. And then followed by a lot of work by Seni and others, actually has a different purpose, has the purpose of locating keywords on encrypted text, but it could be used to process certain SQL queries, such as equality. However, those are only specific kinds of queries, and sometimes database indexes cannot be used, so it's not as efficient as CryptDB. There are also system proposals that result in weaker security and functionality and also efficiency, and many times those require significant client-side processing of the data. So beyond the database server, the client also has to do a lot of data filtering. So now that I explained CryptDB's approach, let's go into the design. So as a system setup, let me remind you that we have a database server that is under attack. An attacker can get full access to the data of the database server, but it's passive, and the application is trusted. There is a second part actually to CryptDB that deals with attacks to the application as well, but I'll just refer you to our paper because it's just an extension to the solution I'll show here. So first, we're going to introduce a lightweight machine called a proxy on the client side, so it's also trusted. So the proxy only stores the schema and the master key. So the schema is basically the name of the tables and of the fields and data types, but not actual data content. So the schema is short. Whenever the application issues a query to the database server, the proxy intercepts it, transforms it by doing certain encryptions that we will talk about soon, and then sends it to the database server. The server processes the queries on the encrypted data completely, then sends the encrypted results to the proxy. The proxy decrypts them and sends them to the application. Note that the proxy doesn't do any query execution at all. It all happens at the database server entirely. Okay, so let's see how do we process queries on encrypted data at the database server, and I'll start with a simple example. So consider we have the table employees at the database server that has 3 columns, rank, name, and salary. In fact, we anonymize the names of the table and of the column. So we have table 1, column 2, column 3. This is what the database server sees. Now, each gray block indicates a data item that is encrypted. And initially, we encrypted with randomized encryption. So for cryptographers, this is semantic security, probabilistic encryption. And the reason is that this is very strong security, very strong encryption scheme. For your information, I am showing the values in the salary column unencrypted, but the server only sees the encrypted ciphertext. Okay, so let's consider that the application sends a query to the proxy saying, give me all the rows where salary equals 100. Remember that our goal in CryptDB was to keep the computation on encrypted data the same as on unencrypted data. So what we would like to do here is to have the database server just do an equality check. But we can see that that's not possible because of the randomized encryption. The encryptions of 100 are different. Okay, so the first simple idea is to in fact use deterministic encryption. So we can see that in this way, the 2 encryptions of 100 are mapped to the same value. Now all that the proxy has to do is encrypt the value 100 with the same encryption scheme and key, and then just send that query to the server. Now the server can perform the equality check on encrypted data as if the data was not encrypted to begin with. Then it sends the encrypted results back to the proxy. The proxy decrypts them and sends them to the application. So what happens if instead the application requested all values where salary was at least 100? We can see that the deterministic encryption scheme doesn't preserve order. So 60 is smaller than 100, but the encryption of 60 is larger than the encryption of 100. So performing a greater than operation won't work. Instead, the idea is to use order-preserving encryption, which are some recent encryption schemes that preserve order. So basically, if 60 is smaller than 100, then the encryption of 60 is smaller than the encryption of 100. Okay, so now again, the task of the proxy is easy. It encrypts the value 100 with this order-preserving encryption scheme, sends it to the server, and now the server can perform the greater than operation on the encrypted data as if it wasn't encrypted to begin with, sends back the encrypted results, and the proxy decrypts them and sends them to the application. Okay, so this gives you an insight into our 2 main techniques. The first is to use a SQL-aware set of encryption schemes. Basically, have encryption schemes that can cover most common SQL operations. And the second is to adjust the encryption of the database based on the queries. So we saw that different queries require the data to be encrypted with different encryption schemes. So we'll have to have a way to adapt, to adjust between those encryption schemes. So I'm going to present each of these techniques in detail. So let me start with the first one. So on this slide, I'm going to show you all the encryption schemes we use. We use 6 of them. And I'm going to show you in roughly decreasing security, but increasing functionality. So the first one is, we call it RAND, which stands for randomized encryption. It's implemented with AES, provides strong security such as semantic security, which basically leaks nothing about the data, but it supports no computation. The second one, we call it HOM, stands for homomorphic. So note that here we're using a specific kind of homomorphism, which is PIE for addition. So this is efficient. Fully homomorphic encryption that supports general computation is not so efficient. So this allows us to support SQL operations such as sum. And the homomorphic encryption is roughly as secure as RAND. It's semantic security as well. It has strong security properties. The third one is search, which allows us to do word search, so to locate words on encrypted texts. And this is just the scheme of Song et al. From 2000. It enables us, therefore, to support the I-like operator in SQL, but a restricted type. Basically, we just support whether there are full word matches. And search is roughly as secure as HOM and RAND as well. Then we have that, which we've seen is deterministic encryption, and it allows us to perform equality type of operations. So therefore, in turn, we can support a lot of SQL operations such as equal, different, in, count, group by distinct, and so forth. And the remaining two are actually some new encryption schemes we provide. The first one is join, and the join is useful for finding equality matches between two columns. And OPE, we've seen order preserving encryption, is useful for order type of operations, which supports a lot of SQL operations such as greater, smaller, order by, sort, max, min, greatest, and so forth. So I'm going to show how to use all these encryption schemes, but first let me discuss briefly about the encryption schemes we provide. Yes?
CMC?
CMC is it's just a mode of using AES. Basically, one of the encryptions streams into becomes the IV for the next encryption, and you also go backwards. So you go one direction and you go back. It basically allows us to provide the security property that once, which is pseudo-random permutation. Okay, so for join, we basically for join, what we want is we want to have equality checks between two columns. Okay, so why can't we use that for this deterministic encryption? Why do we need a new encryption scheme? Well, here's the problem. We don't know ahead of time what columns will be joined. So there are two possibilities. One is we encrypt all the columns with the same that key, in which case the server will be able to do the joins. But that leaks more than we intend to, because there may be times when the user doesn't request joins between two columns. And CryptDB's goal is really to only release those relations among data items that are needed for the types of queries issued by the user. So that would leak more. The other choice is to have every column encrypted with a different key, but then when a join is requested, the server cannot do it. Instead, our scheme allows us to initially encrypt the columns with different keys for security, but then when the application requests a join between two columns, the proxy can give a token to the database server, and using that token, the server can adjust the encryption of the two columns to an encryption with a common key. And then the server can just see equality matches. Okay, so let's see in more detail what kind of encryption scheme do we need. And this encryption scheme has 4 algorithms. The first is a key gen, using which the proxy can obtain a secret key. Then the encryption algorithm allows the proxy to encrypt a value, a message M, for a certain column I using the secret key. Then when a join is requested, the proxy can compute a token for 2 columns, column I and J. And then it gives this token to the server. The server now uses the 4th algorithm, the just algorithm, with the token from the client to transform the encryption of a column to an encryption with a shared key, as the figure shows. So now, since the 2 columns are encrypted with the same key and the encryption scheme is deterministic, the database server can figure out equality matches and can process the join. So our join scheme, we have a report online with security definitions and proof, but intuitively the security says that the database server cannot learn join relations without knowing a token. And we implemented the scheme actually in elliptic curves, which means that the ciphertexts are rather short, considering it's a public key scheme. So they're 192 bits long. And the time to encrypt and to adjust is half a millisecond, which is reasonable. Okay. So the second encryption scheme we come up with is OP, order preserving encryption, which I think is the more interesting one. And remember that order preserving encryption aims to reveal the order, but ideally it should reveal nothing beyond order. So this was formalized by Boldereva, Chenet, Lee, and O'Neill in 2009. And the security notion was called IND-OCPA, indistinguishability under order chosen plaintext attack. What basically this security notion says is that no adversary can distinguish between encryptions of 2 sequences of values that have the same order relation. Well, it turns out there have been more than 10 order preserving encryptions proposed, and they actually all leaked more than this ideal security. They leaked more than order. And part of the reason why this has been so difficult is that BCLO showed in 2009 that such security definition is infeasible. And more concretely, what they showed is that the size of the ciphertext has to be exponential in the size of the plaintext. So if you want to encrypt 32-bit values, then the plaintext size will have to be 2 to the 32 bits long, which is huge. In fact, we showed an even stronger impossibility result that there simply is no Windows CPA OP scheme, even if you want to encrypt 3 values. So in that case, 2 to the 3 wouldn't be so large as a ciphertext, but it's actually not possible.
Sorry, is this in the standard model?
The impossibility? Yes.
So in our normal
I doubt it because it's a property of the resulting function. So basically, basically what we show is that there exists an adversary such that the advantage of the adversary is 1 over the ciphertext size. So no matter what scheme you come up with, the advantage of the adversary will be 1 over the ciphertext size if the scheme is order preserving. So, okay. As a result, the BCLO paper, they settled on a weaker security definition that later turned out to actually leak half of the plaintext bits. So not only leak the order, but actually, given a ciphertext, you can tell the highermost half of the plaintext bits. And order already leaks quite a bit, so we really didn't like this. We really wanted to have ideal security. And the observation we made to achieve that is that, in fact, in a real system, such as a database, the model is less restrictive than the one of an encryption scheme. In particular, you can update ciphertexts. So you can go in, if you encrypt a certain value and place it in the database, at the later time when you encrypt another value, you can go back in the database and update that value. In a real system, you can do that. So we call those mutable ciphertexts. So it turns out that with a small number of ciphertexts, if a small number of ciphertexts are allowed to change, then we can achieve ideal security. And in fact, we also show that this mutability is in fact necessary because we showed that any Indo-CPA scheme is infeasible without mutable ciphertext, even if the scheme is stateful, meaning that the encryption algorithm can look at all the history of values encrypted before, and even if the encryption algorithm can run for a really long time, not even polynomial, it's still infeasible without mutable ciphertexts. But if you allow a little bit of mutability, then you can achieve ideal security. And in fact, you can achieve an even stronger security definition that we call same-time security. So what we mean by this is that the order should only leak about among items that are currently in the database. So for example, if an item is old and was discarded and a new item was inserted, their order relation should not leak. Whereas with Indo-CPA, the order relation leaks among any items ever encrypted. So, and also in a real database, really, the database server only needs to know the order relations among items currently in the database. It doesn't need to learn more than that, so there's no reason to tell him more order information than that. Okay, so let me tell you briefly the gist of our scheme. Yes?
So your definition, does that allow for an adversary who watches as you're changing, who watches which ciphertext you're changing as you're adding new ciphertext?
Yes.
So it's to see the entire process?
Yes, yes, and it's simulation security as well. It's not indistinguishable. Yes, it's adaptive in that sense. Okay, so and probably that will be clear when I show you the gist of the scheme. So the server stores a binary search tree of values. Okay, so each node contains the deterministic encryption of a value. The deterministic encryption, basically, for cryptographers, is as strong as pseudo-random permutation, basically. So it leaks strictly less than order. Okay. So what is the So in this binary search tree, the values are sorted based on their underlying plaintext. So the left child of a node has a smaller plaintext than the parent, and the right child of a node has a larger plaintext than the parent. Now, the order preserving encoding, in our case, is actually given by the path in the tree. And the reason is that this path naturally indicates the relative order between the items. So, for example, the path of 12 is 0, 0. The path of 48 is 0, 1. Now we actually have to pad this path because the root has an empty path. So how does the empty path compare to 0, 0, or 1? So we actually pad it out by adding a 1 and then as many zeros as needed to pad the value. Okay, so let's see. Therefore, the OP encoding of the value 12 is 0, 0, 1, 0. Of the value 48 is 0, 1, 1, 0. And of the root is just basically the padding because the path is empty. And we can see that these values actually preserve the order. So how does the proxy encrypt the value, let's say 32? Well, it first provides the deterministic encryption of 32 to the server. And the server says, well, the server doesn't know what the plaintext values are, so instead it replies with the root of the tree. Then the client decrypts that value, sees that 32 is to the left of 50, so it tells the server, okay, go left. Now, the server gives the client deterministic encryption of 23. The client decrypts it, again, sees that 32 is to the right of 23, so it tells the server, okay, give me the value on the right. And so forth until they find a place in the tree that's empty, and at that place, the server encrypts the new, inserts the new encryption. All right, so we can see that all the information that the client provides to the server in this case is just left or right, so it's just order relation. Nothing in addition to order relation. So intuitively, you can see why we achieved the definition, but I won't go formally into it. Okay, but what happens if the client keeps asking for values to encrypt along a certain path? The path grows really large, which means that the ciphertext size becomes large. And this starts to remind us of the infeasibility results we talked about. But that's precisely where mutability comes in. We rebalance the tree. When we rebalance the tree, certain ciphertexts may move in the tree. Now, if they move, they have a different OPE path, which means they have a different OPE encoding, and we have to go and update the database. That's how mutability makes us avoid this infeasibility of large ciphertexts. Okay, but it turns out that the number of ciphertexts we update per encryption is actually small, is logarithmic. And we implemented this scheme, and surprisingly, it was 1 to 2 orders of magnitude faster than the BCLO scheme, which was the most secure encryption scheme previously to ours, and it leaked half of the plaintext bits, more than us. All right, okay, so, yes?
When comparing to BCLO, your scheme has these round trips, right?
Exactly, they're included.
Oh, so even including that network?
Yeah, of course. The question is how much network do you include? And we have a graph in our paper showing that basically the dependence on the network and the point at which BCLO becomes faster. But one thing to say about BCLO is that if you encrypt values beyond 32 bits, the scheme becomes extremely slow. So the performance of the scheme degrades a lot by the number of bits you encrypt. So for message size of 128 bits, it's not even, you have to have really large network too. And another thing I want to add about network is that our scheme actually is parallelizable. So you can encrypt things you can encrypt things in parallel. And basically network cost is not really factored in at that point. But yeah, sorry.
What happens if you relate this to the real world? Let's say I'm trying to track you down. I know that there's a lot of Smiths in the database, and you're in front of them. And there are even some Robinsons. And then maybe I code an update on Pomerantz and Porter. And now I've bracketed you, right?
Right, so basically, order preserving encryption leaks order. If you can use order to learn what an item is, for example, if, as you say, you bracket two things, then yes, you can learn. I'm saying order preserving encryption leaks something, so yeah. But I'll show you one thing that in practice actually, very interestingly, very sensitive fields will remain encrypted with RAND, which leaks virtually nothing. But I'll get to that. I'll show you real applications and what happens in that case. And the OPE really is used for less sensitive fields. And in fact, if you're concerned as the owner of the data, you can always put thresholds saying, don't go to OPE and don't use OPE for this data. But we're going to get there. Yeah.
Is that server that does this OPE?
It should be on the database server as well.
Is it stored as a B tree? How is it stored?
It's stored as a bit tree, yes. Yeah, memory and backed by disk.
So the threat model is the system administrator himself. What's stopping him from creating another proxy?
Oh no, so the proxy is, if you remember the model, the proxy is considered to be trusted is on the application side. Here.
Picture,
Nothing is trusted here.
but your server is actually trying to.
Yes, it's a passive adversary. Passive meaning that I'm trying to learn as much information as I can, but I won't do things incorrectly. I won't change queries. I won't change database content.
So again, I mean, if I have access to the server, I can create a proxy. I can mimic a proxy near on the server.
You cannot create a. Okay, so this proxy is on the trusted side, and it has the master key. Okay, master key. Now, if you have create a new proxy on the server side, you have to give it some key. It's incompatible with the other key, and you get junk bank. But yeah, the proxy is on the application side is trusted. As I mentioned, we have a second part to CryptDB in which we deal with attacks to the proxy, and I can talk to you more offline about that if you want. Yeah.
So the encryption. So here is the encryption of 32. Here is the 0101.
Yeah.
But here all these. Also, you already encrypted 32 with your deterministic encryption.
Yes.
And then you.
Yes. Okay.
I just have one question with regard to the picture you showed before. So if the database administrator wanted to change the schema, is the proxy at all involved in that, or is it just a cache for the schema?
So if you want to change the schema, I guess it depends how you want to change the schema. If you want to add another column that's sensitive, you've got to encrypt it. So you've got to use the key of the proxy to do that. So it really depends on.
So shouldn't the proxy be under the administrator's control too, in that case?
Okay, so there are two. Okay, so there are really two types of administrators. One is the system administrator that just maintains the system servers, like manages load. If a server crashes, boots up another one. That's separate from the database administrator. Okay, now there can be database administrators, and it depends on how much trust you're willing to give them. Depends on what kind of work you're willing to give them. If you really, it's crucial to allow them to perform all kinds of queries and even to see the database in the clear, then sure. But if they're only for certain maintenance reasons there, then you can even protect against those kind of administrators.
So where is the key stored in the key?
In the proxy only.
And the proxy is running along with the application, along with the server.
Yes. On the trusted side. Okay, so let's go to the fun part. Now we have all these 6 encryption schemes, and the question is, how do we use them? Well, one possibility is we can encrypt all the data with all of them, because it's important that the queries that come in, so the encryption schemes that we use depend on the queries that come in. Certain queries need certain types of encryption schemes. And the problem is that we may not know the queries ahead of time. Therefore, one naive solution would be to encrypt the data with each of these encryption schemes so that we can support all the queries that would come in. But that would be a space waste, but not so much that, as much as the fact that each column is encrypted with OP, which leaks order. And in fact, an application may never perform an order operation on a certain column. So in that case, according to CryptDB's goal, we should not leak the order relations on that column. So instead, our idea is to stack the encryption schemes into onions of encryption. So each value becomes encrypted with 3 onions. So the first onion encrypts the value with join, then the resulting encryption with that, and the resulting encryption with rand. So we can see that this onion is useful for equality type of operations. Now we can also see that as you go down in the onion, the functionality strictly increases. So join can process the same way as that, but in addition can also join with a different column. Now the second onion is onion order, which encrypts it with value, OP join, which I didn't tell you about, OP and rand. So it's useful for order type of operations. And the third onion depends on the type of the field. So if it's a text for search, for keyword search, if it's an integer for homomorphic addition. Each of these, all the values in a column are encrypted with the same key, but the key is different across different layers of the onion, across different onions, and across different fields. Also notice that initially, when the onions are in this state, the outer layer of the onion is rand, search or home, which are semantic security. So basically, it leaks nothing about the data in this state when we start out the database. But then as queries come in, we need to adjust the encryption scheme to support those queries. And this happens naturally with our onions. We just peel off layers of the onions. So the proxy gives a key to the server using a SQL user-defined function. So these are basically functions that the SQL interface allows the user to define, and they can be invoked from within a query. Now the proxy remembers the resulting onion layer for every column, and we do not put back that onion layer. So for example, the first time we do an equality and the layer is taken to deterministic encryption, then all future equalities on that column don't need any further decryption, they can process directly. Yes?
So if you're running a UDF function that has access to a key, an administrator can just run a profiler that keeps a workload of queries. Can't they get access to the keys?
Okay. So there's a key. Okay. So getting access to the key for a layer tells you nothing about all the other keys. So there's a key per layer that is different for every layer. So once we give that key to the server removes that layer, that key is useless for any other purpose. In fact, the server can even look at it and use it, but it's useless. Okay, so let's see a concrete example, again on the employees table. So each column becomes 3 columns, 1 for each onion. Within each column, a value is encrypted with onions of encryption. So for example, CEO in the onion equality is encrypted with join, that, and rand. Now consider that the query comes at the proxy requesting all values where rank equals CEO. The proxy says, okay, it's rank, so let's look at the first column. It's an equality, so let's look at onion equality. And then the proxy remembers that the outer layer for that column is rand. So remember, for rand, we cannot just do an equality, so we need to adjust it to the deterministic encryption. For that, the proxy issues an update query to the database server, invoking a decryption UDF and giving the key only for the rand layer, so for that layer alone. Now, executing this update query, the database server removes the rand layer, and the outermost layer now becomes that. Now, the query is processed as before. The proxy encrypts the value CEO with join, and on top of that with that. And now the database server can perform the equality on the encrypted data as before, as on unencrypted data, and return the results to the application decrypted. All right. So we saw how CryptDB works. Let's talk about the security guarantees. So we saw that depending on the queries, we pick the encryption schemes, and they have, and each encryption scheme may have a different kind of leakage. CryptDB makes two kinds of guarantees. The first is that the system design of CryptDB with the onions guarantees that the encryption scheme exposed for every column is the strongest encryption scheme from our encryption set that enables the query. Now, overall, intuitively, CryptDB only reveals the data items needed for a type of query. Okay, so the way we formalize this cryptographically is similar to secure multi-party computation. You have a real and an ideal setting. In the ideal world, there is an oracle that helps the server process the queries. For example, the server asks the oracle questions such as, is the item in the second item in the first column equal to the third item in the second column? And the oracle examines whether the answer to that question is needed for the query the server is processing, and if so, it tells the server the answer. Okay, so clearly in this ideal world, all that leaks, all that the server learns is what the relationship he's allowed to learn. And now we prove that the real world with CryptDB and the ideal world are computationally indistinguishable. Yes?
Most database operation can be optimized various ways, and you ask different questions for each of them. Do you have any proof that?
No. The proof is, if you look at our technical report, we prove that for each specific operator, the way the query is written out, each requires certain known operation. Yeah, no, not the way you could rewrite it, for the fixed query that we get as input. Okay, so but let me show you some natural examples. So if we perform an equality predicate on a column, then that is exposed, which means that repetitions within that column leak. So the server can now see whether the third item is equal to the fifth item, but not their actual values. Now, if no aggregation is performed on a column, then, now if an aggregation is performed on a column but no equality or inequality, then homomorphic remains as the outer layer, which is semantic security, which virtually leaks nothing about the data. Also, if we perform no filter on a column, we don't do equality, we don't do inequality, we just fetch and retrieve the data, then the outer layer remains rand, which virtually leaks nothing about the data. And actually, it turns out that this is very common in practice with sensitive fields, as I will show in some application examples. And the bottom line is that we never decrypt the lowest layer of the onion, the OP, so we don't reveal plain text to the server. Yes?
Once you move one layer,
yes.
are all future inserts
yes.
Going to be on the same layer, or you will reset them to the original?
On the same layer.
The same layer.
Yes.
So you stay there.
We stay there. You can envision, obviously, security optimizations by refreshing it, periodically. But it's cleaner to describe it this way. Now anyone can improve it the way they want.
Can you put two different kind of onion? If you, let's say, pose a certain kind of query, you pose a completely different kind of query. There are two kinds of onions for this data.
And
can you put these two together and get to the plain text?
Basically, you're saying if some onion, if some onion leaks something, another onion leaks something else, can you somehow correlate and learn something? Depends on the setting. Maybe you could. The point is that we leak equality for deterministic and leak order for. Okay. But as I said, I'm going to show what happens in practice. And in fact, for most sensitive fields, it remains encrypted rand, which you cannot correlate with anything. So basically, these two cannot be correlated with anything. Okay, so
In your model, the adversary can't influence the type of query that gets executed.
It's a passive adversary, yes. Yes. But let me say that, in our second part of CryptDB, we actually consider active adversaries, and we even consider adversaries that attack the proxy. And there, we're able to provide guarantees of the following. If a user is not online at the time of an attack, then his data is not compromised. But if he's online at the time of the attack, then his data could get compromised. So we limit the compromise in the situation when everything is compromised and actively as well.
Yeah, I was just thinking of an adversary who could force these sort of queries to be executed on the whole database, then all the layers come off and everything's visible.
Right. So that's why we say this scheme is for a passive adversary. Now, if you consider an active adversary, basically our second part of CryptDB, which requires more explanation, but it guarantees to you that if you are offline during an attack, then your data doesn't get affected, meaning that an adversary could not get your onions down, because when you're offline, your data basically your key will not be available, will not be even at the proxy at all. And when you're online, your key can be at the proxy. Yes, the adversary could lower them down to the onion level, and we don't guarantee, but yeah.
Naively, I would expect lots of queries to have sums or averages, and maybe I would expect homomorphic encryption to being a publicly operated to be pretty expensive. How do you keep things down to 26% penalty?
We'll see the exact breakdown in costs. I will show you the exact breakdown for every query in cost. You're right, that's the most expensive operation, but we do have some optimizations, and we'll see the exact numbers.
Back to this point about active adversary. So if you have a passive adversary, this look, the data and the queries are chosen in your definition. Right? The data and the queries are chosen by the adversary.
That's not passive.
So it's passive in the sense that so another way of phrasing is that your security guarantees, right, are hold for any data set and queries, right? Like when you define security,
right?
I'm assuming you're saying like for all databases and for all queries, right? Like you're not assuming some distribution on the data.
No. So basically, no. But we're not saying. Yeah. So our security guarantee doesn't say CryptDB doesn't leak anything. Our CryptDB it doesn't say that. In fact, our security guarantee says CryptDB leaks only what is needed to process the query. Equality if you need it, order if you need it. If you don't need it on a certain column, then nothing.
And this holds for any data sets. It's not. There's no assumption about it. There's no distribution over this.
No distribution over data.
Security words for all.
Exactly. Yeah. No distribution at all. You had a question?
I'm thinking Sartor might be here.
So you chose this layering model.
Yes.
Why didn't you actually encrypt it in separate using, rather sort of use each layer and encrypt the data and maintain different copies? So use a deterministic encryption of the data, a random one, a joint one, and keep them separate rather than...
Yeah, so you're right. So the reason why we didn't do that is because then each data would be encrypted with OPE, which leaks order. And we don't want to leak order for a column unless order is needed for that column. And we don't know ahead of time what are the queries, so we don't know ahead of time if the order will be needed. Therefore, we want to start initially with rand being the outermost layer, leaking nothing. And then if the user actually needs order, then we peel off the level.
Well, what I'm saying is keep an OP data and keep a rand data as well.
On top.
Not on top, separate. So when the proxy issues a query, the proxy says, oh, for this query, I don't need the op encryption, I only need the rand one. So I just go to the rand.
Right. But the question is, what does the server know? If the server has the OP encryptions of the data, then he knows the order. So if the server has the OP encryptions of a column, then he knows the order. And we don't want him to know that until we need the order for sure.
But he also do something. I mean, I understand that. You're right. Okay, then let's take this offline.
Okay, so we implemented CryptDB on top of MySQL. And one of the cool parts of CryptDB is that we didn't make any change to the DBMS. And the reason is that we could not make a change is because we used user-defined functions. So basically, whenever we wanted to change the behavior of the database server, for example, decrypt something, then we invoked one of these user-defined functions. And this makes CryptDB portable. In fact, our initial implementation was in Postgres, and we moved it to MySQL with only 86 lines of code change to CryptDB. And that was mostly into the interface of the UDFs and how you talk to the server, not really anything to the core of CryptDB. Yes?
This includes your encryption scheme? Your OP is designed to seem to require some code, server code change, server code, right?
No, actually no, because so everything, all that tree looking up, can happen in a UDF, in a user-defined function. Yes, the DBMS doesn't change at all. And in fact, it doesn't even have to be restarted, because you can load the UDF libraries dynamically.
The B-tree structure which you use is the MySQL B-tree?
No, it's...
you build your own B-tree?
Yeah.
And that's also done as part of your UDF?
Excuse me?
The B-tree construction is also done as part of your UDF?
Yes. Okay. Also, there is no change needed to applications because the CryptDB proxy exports a SQL interface. So existing applications can run on top of CryptDB unchanged. Okay, so we evaluated CryptDB, and in doing so, we tried to answer 3 questions. Does CryptDB support real questions and applications? Real queries and applications? What is the resulting confidentiality in terms of the onion levels? For example, the questions you guys have been asking me. And what is the performance overhead? So in terms of real queries and operators, we don't support all queries. For example, we don't support complex operators such as trigonometry, and sometimes we don't support combinations of encryption schemes that we support. For example, A plus B greater than C, we don't support because to do A plus B, you need to do homomorphic encryption, and then to compare it to C, you need order-preserving encryption. But homomorphic encryption does not preserve order. There are things you can do to support these queries as well. For example, you can split the queries into 2 queries and have the client re-encrypt, for example, decrypt the homomorphic result and re-encrypt it with OPE, or you could pre-compute columns, or you can use FHE for specific types of computation. And in fact, there's a project at MIT that's follow-up to CryptDB that does all of this and is able to support virtually all the queries at the cost of some computation on the client side. And in terms of real applications and queries, so we looked at 7 real applications, out of which I'm showing you 5. So PHPBB is an open source forum software in which we'd like to secure private messages, for example, or private posts. HotCRP is a conference management website for SOSP, for stock, in which we'd like to hide reviews, paper authors if it's anonymous, and so forth. GradApply is the MIT graduate admission database where we'd like to hide student grades, letter of recommendations. TPC-C is an industry benchmark, and SQL@MIT.edu is a large trace of queries we got from a popular SQL server at MIT that hosts thousands of applications, and this trace is over 126 million queries and more than 120,000 columns, because we wanted to see really what does CryptDB support or not.
Why don't you improve the columns?
Right. So in these applications, we only encrypted the columns that we deemed sensitive. So we evaluate which were sensitive, such as posts, such as secret posts, secret messages, things that seemed sensitive. Whereas for the traces, we said, let's encrypt everything, even if they didn't seem sensitive at all, just to see how CryptDB would perform in that situation. But the realistic situation is the one in which you only encrypt the things that are sensitive. Basically, for the large traces, almost nothing was sensitive for TPC-C, but we said, let's see what happens if everything is encrypted. And actually, the good news is that for the applications, we supported everything on the encrypted data, on the sensitive fields, and for TPC-C, we supported all the queries on all the fields because we encrypted them all. Now, for the large query, we didn't support 1% or less than 1% of the queries or less, and that was and those were queries like this, queries that were doing actually mathematics in the SQL query. So select 1 over log of okay, so those we couldn't support.
So this is queries, it is number of columns.
Yes, number of columns. Sorry. Yeah.
What about all these 500 unencrypted columns in the database? You're happy leaving them in plain text?
So yes,
Okay.
we examined which ones were sensitive. In fact, we were even exaggerating. For example, if the posts were private, we definitely were keeping it as private, but we also kept as private the date when it was posted, everything. And this is the number of values we got. For example, there are a lot of fields such as auto increments that the database server obviously knows what they are. There's no point to hide. And yeah. Okay, so how about the resulting confidentiality level? So we examined the mean level for every column. What the mean level is the weakest encryption scheme exposed for that column. So we can see that, in fact, most of the fields remain at rand, which means that nothing leaks about those fields. The reason they remain at rand is that there's no equality or inequality performed on them. They're basically just inserted, retrieved, maybe based on other fields. Or maybe summation, again, that one doesn't leak anything as well. So that is the good news about CryptDB. Now, some fields were at OP, which is the one that worries you guys the most, and me as well, because it leaks order. But very few fields were at OP, and in fact, we examined manually to see what those fields were, and they look to be less sensitive. For example, the contents of a post were all at rand, but the time when the post was made was at OP.
Is this based on, did you examine a trace of queries over time to see?
We examined all the possible queries that this application can issue, which is easy because it's a fixed set, because these are web applications, and also for TPC-C. And for SQL, we examined 126 million queries in a stream. And we couldn't examine whether these were sensitive or not, because there were too many.
So did you just look at the SQL queries, or did you look at the stored procedures and the code outside it also? Like TPC-C has not just SQL queries, it has a bunch of logic around it.
TPC-C or TPC-H?
TPC-C. TPC-H is just statements.
Right. So
TPC-C has stored procedures.
Right. So we take the benchmark SQL is a benchmark for TPC-C on GitHub, and we run that on top of CryptDB. And
Just look at the queries.
yes, just look at the queries. But that's what.
TPC-C has certain like additions for it. So I would expect to see your failure scheme, but I don't see any columns encrypted using the failure.
Using the
partial homomorphic addition failure function.
Oh yeah, because the mean level in that case, you're right. The mean level in that case is rand, is hom, which is as secure as rand. So I'm including them all under the column. And I think I even said that all these items here are either not, you don't do equality or inequality, or you just do addition. So they're included here because the same security. Maybe I should have said more clearly. But yeah, CryptDB certainly does. TPC certainly has a few of those.
If you just run statements, then you're not measuring. TPC, you're not measuring the number of transactions. You're measuring the statements per second.
Yes, queries per second. Okay. So in terms of performance, let's compare the performance of CryptDB, of applications running on top of CryptDB, to applications running directly on unencrypted MySQL. And we looked at a lot of metrics in our paper, but here I'm just going to present you the two we consider most interesting. So one is the latency, that is the time from when an application sends a query to the time it gets a response. And the second is server throughput, the number of queries per second the server can process. So in terms of latency, CryptDB adds on average 0.62 milliseconds per query for TPC-C.
Is it because the workload is disk bound?
Because the workload is?
Disk bound?
No, it's because of the encryption. The delta is because of the encryption.
I'm saying that the gap is so small because the workload is disk bound. There's not much memory in the system. But what's the size of the database?
The size of the database, it fits in memory. It's in my memory. It's encryption cost. It's encryption cost. Yes.
Well, you have the space a lot, right? So.
Right. And I think for TPC,
You could see a larger difference between clear text and encryption. Because
yes.
You have to read a lot more data.
Probably. So the
you ran warm numbers, so it's all fitting in memory.
It's all fitting in memory, and the encryption overhead in terms of space expansion, I think, is 3 times. 3 times. We have more precise evaluation in our paper. Okay. So in terms of throughput, yes.
For some of your operations, you have to go through multiple iterations between the proxy and the encrypted database. What is the assumption, if you go to the previous slide, what is the assumption that you made on the latency between the CryptDB proxy and the encrypted database?
So the application, so you're saying that it has to do a bunch more round
Well,
trips?
so for example, if the encrypted database is held externally and the CryptDB proxy is on the same machine as the application, then there may be a large latency between the two machines.
So our setup was the following: application, CryptDB proxy, and database all on the same machine, 1 core. We restricted the machine to 1 core so that we don't see other behavior. Okay. So in terms of throughput, this graph shows the queries per second as depending on the number of server cores for TPC-C, for MySQL, and for CryptDB on TPC-C. And the maximum throughput loss is of 26%. So let's understand why. Yes?
So that includes updates as well, or is it only queries?
It's all of TPC-C, which includes updates, deletes, everything. Okay, so if this graph shows you the throughput for different kind of operations of TPC-C, so we see delete, insert, for MySQL and CryptDB. So we can see that actually for the first part of the queries, actually the throughput loss is less than 26%. And the reason is that, in this case, the server doesn't do any cryptography in a steady state. So here's why. Once you do an equality and you lower the onion level from rand to that, then all future equalities processed directly on the data. They don't need any additional decryption. So in that sense, the server here does the same work as an unencrypted database, except that the tuples are a bit larger because of encryption. So the cost that you're seeing is the cost of the expansion because the values are a bit larger because of encryption. Yes?
But there is an overhead in as much as the levels of the onion have to be undone. So there's the proxy DB still has to do multiple encryption, not just a single layer. It has to do every layer underneath.
So there's a steady state on this. There's not any.
Yeah.
This
So
is
that's that difference.
So this is server throughput, which means that it's the number of queries per second at the server. It has nothing to do with the proxy.
This doesn't represent the.
This does not represent what
load
represents.
that's on.
No, what represents the proxy is actually the latency. The latency difference, because this latency includes the cost of the proxy and everything.
Yeah,
But good question.
With respect to latency, did you say that was median latency?
That was average latency. If you want to know the exact breakdown, our paper has precise breakdown. Okay. So the second part comes back to your question. The second part actually, we can see that update with increments and summation actually have a larger throughput loss than 26%, roughly 50%. And that's because the server is doing homomorphic addition pi-e. So instead of adding 2 values, it multiplies some larger cryptographic numbers. But overall, on TPC-C, the throughput loss is of 26%, which we think overall is practical. Yes?
Your Writing to the log, right? The database log. I guess you have the log turned on, right? It's a transaction log.
I don't think so.
Because you have to, because there's a database, you'll be turning on a transaction log. And so that for the updates, you have to incur, even if your data is sitting in memory, you have to incur an I/O cost to write to the log. And as I/O cost would be a lot more for.
Okay, so we did not disable the log. We did not disable the log, and the MySQL setup was the same for CryptDB as for plain MySQL. That's what I can tell you.
Okay, so what engine were you using? Were you using InnoDB or?
I think we were using MyISM or InnoDB, actually.
Does it have login?
I see. Because
The point is that we used the exact same setup for both of them, so we did not make any changes.
Logging would be important because if the data size blows up, those are directly reflected in the log. So you're doing 3 times more I/O. And logs have to be persistent, independent of whether data is in
That's why you get the guarantees of a database system, right? You have to have the log.
I agree, and we didn't disable the log.
So when you talk about powered up preserving encryption, you showed us the James encrypted tree, and you are doing rebalancing. When you rebalance the tree, that means that you have to go rewrite the data.
Yes.
And that's also factored in your insert process.
Okay, so basically this CryptDB, so these are 2 papers merged into one talk. So the CryptDB paper contains a scheme of Boldireva et al. That's the one it includes. So basically there's no tree rebalancing, but at the same time the encryption cost is larger. So 1 to 2 orders of magnitude. So these results are for CryptDB. Now the OP scheme I told you about is a separate paper, actually follow-up. So, but it would indeed be very interesting to try to put them all together and see.
So what happens if there's a wide area link between the proxy and the server?
If there's a wide
area link between the proxy and the server, because that's probably the most secure setup.
Yes.
If it's on the same server, if it's in the same data center, the system administrator can still have access to the page.
Right. So the proxy and application are supposed to be not accessible to the database administrator. So
he's saying that if the link between the proxy and the server was a wide area link,
yeah,
then your latency would increase.
Right.
And if you had multiple round trips, the latency.
Right. But the latency should not affect server throughput. We're talking about how many queries per second can the server, while being choked, support. Okay, so I have a demo for you guys. Short CryptDB demo. I hope it displays properly because we had some problem with the projector. Okay, so it seems like it does. Okay, so on the, I need to get my cursor. Okay, so on the left side, I have a shell to CryptDB. So this is, for example, what an application would use. The shell exports SQL interface, so things should work exactly the same. On the right side, I have I have a shell into the MySQL server, so you can see what exactly gets stored in the database. So let's create a table, and I'm also printing out messages to see what's happening inside CryptDB. So I create a table that has 2 fields, name text and age integer. Now this gets transformed into create table 0, and you can see the det onion, OP onion, the search. There's some salt because we use a yes salted, and that's a separate field in itself. Okay, so for example, we can check that the database server indeed, that's the table that gets created. Okay, so 3 onions for each field and a salt. Okay, so now let me insert into the table Alice, age 19, Bob, age 21, Chris, age 20. So we can see that, in fact, what the CryptDB proxy produces is really a query with encrypted values. And let's make sure that that's what's getting stored at the database server. So indeed, we can see that the database server contains encrypted data. Okay, so now if the user wants to, see what's inside the table, we can see that he still gets access to the decrypted data. And we see what actually the proxy does behind the scenes. So it tells the server, okay, give me all the equality onions because those are easy to decrypt, and the salts. Then it gets back the encrypted results from the server and decrypts them and gives them back to the user. Okay, so let's do an onion adjustment. So we can say select star from T where age equals 19. Okay, so we can see that the first, as I said, the layer is rand initially. So to process the equality, you have to go down to that. So we can see that an update of the onion equality gets issued, and the level therefore becomes that. Then the actual query is issued. We can see where the that field is equal to the encryption of 19. Then the encrypted results are received from the encrypted results are received from the database server, and the proxy decrypts them and sends them to the user. Okay, so now I'm going to show you a more interesting query. So I'm going to select sum of greatest of age and 20 from T. So basically, what the greatest operator does is it takes the maximum from age and 20. So the ages we have is 19, 20, and 21. So the greatest operator will return 20, 20, and 21. And then it passes them to the sum operator who's supposed to add them up. But the first sight, you'll say, wait, didn't you tell us that CryptDB cannot combine encryption schemes? Well, it turns out that our rewriter is really smart. And in certain cases, you're not actually combining encryption schemes. You can use the greatest operator to figure out whether age is greater than 20, but then if that's the case, you return the homomorphic encryption as opposed to returning the order-preserving encryption. So we can see first that it works, and second, we can see how the query was rewritten. So basically, the greatest is transformed into if the OP encryption of age is greater than the OP encryption of 20, then give me back the homomorphic field, otherwise give me back the homomorphic encryption of 20. Now these are passed as inputs to the aggregate user-defined function, which basically does homomorphic addition. And the encrypted result is sent back to the user and decrypted to 61. All right. So in conclusion, if I can conclude, yes, I can conclude. CryptDB provides the first practical DBMS for running most standard queries on encrypted data. It has a modest overhead and makes no changes to the DBMS. This is the website of CryptDB. It has the papers and the source code to play with if you're interested in. And thank you. Yes?
So I have a question about usability. So. Yeah. Encryption is kind of hard to understand for even cryptographers, especially when you throw in deterministic encryption and OP encryption, which some cryptographers probably wouldn't even say is encryption. So what kind of administrator do you think that administrators can understand the implications of using deterministic encryption, or God help them, an OP encryption?
I think. I personally think it's not that hard because these things are just three very simple things to know. One, nothing leaks. One, you can tell them histogram equality, and one, order. So there's really just three things they have to get their head around. And one way to do them, and we've been thinking about it, is to have this nice user interface, basically showing each onion basically on three gradient colors, which one is OP, which one is one equality and one rand, and they can understand based on that the security. But I think the safer thing to say is that whenever they have some column, they know it's sensitive, then in CryptDB they can set a threshold in the proxy, say don't go below rand, and period. So if they're really worried about a certain encryption scheme, a certain column, then they can only set this threshold and say, I don't want to. This is secure, I don't want you to, this is really worrisome, I don't want you to go beyond a certain onion level. But
might it be more, I guess you have hotcap as an example.
Yeah.
So I'm concerned that a steering committee who maybe isn't in cryptography might think, okay, well, we have two alternatives. We could use CryptDB, which I've read about, it encrypts things, it's secure, or we could require the PC chair to have his papers in a separate database. And it seems like
on the separate database on the same server?
Well, I think you talked in the paper about how some hot crap installations go to extreme lengths to keep the PC chair from seeing his conflicts. And so extreme lengths of you having a different database for those.
Right. So
how does the steering committee make those choices?
Right. So I don't think you have. So I think besides CryptDB, you have no choice. You either keep the data, you process on unencrypted data, or you use CryptDB. So I don't think there's really a choice. There's no alternative.
You could say all your PC conflicts are managed by the co-chair, in a separate database.
Right. So you mean right? But that database itself, you compute on unencrypted data. So that one can be attacked as well.
You don't give the PC chair administrative rights to that one.
Right, but you can still potentially have attacks to that database. So now.
Yeah,
now if you're thinking of, I mean, you can always have some sort of attackers and anything. So, but
we have a particular attacker in mind. But the PC chair might accidentally or might arrange to figure out information about.
So if the whole world is only about specific attacks, then maybe you can have solutions only for those specific attacks. But I think the whole world is more complicated, and then I just see two solutions. One, you compute on encrypted data, in which case CryptDB is the only practical DBMS out there for that, or you don't, in which case you don't have the security of computing on encrypted data.
One more follow-up about usability. Might it be better not to have OPE at all, because doesn't give the illusion of security where no such security really exists? It seems like it would be better to just say, hey, administrator, put it plain text, put an exclamation point, say, administrator, anybody could decrypt this column. But saying it's encrypted with order preserving encryption kind of provides a misleading sense of.
So basically you're saying you could have a CryptDB that only contains random and home that leak nothing, and you can have deterministic and join that leak less, and that's it.
Yeah, it seems like the benefit of OPE is, it seems like it's like giving a handgun to a child.
Yes.
It may be more dangerous than value.
I see, because you're saying that the administrators may not understand. Okay, maybe then that's a good idea for the administrators to just tell them, to think about nothing or that. Or in fact, you can make it even simpler for them, depends on what you're willing to assume they can do. For example, you can say, if something is very secure, is very worrisome, mark it as such. For those, behind the scenes, the CryptDB proxy is going to make sure that rand and nothing else. And for the others, it's going to do OPE that, best effort, better than nothing, better than not encrypting, you can do that OPE. But maybe for the administrators, they could just point out what's secret and what's worrisome and what's not. That will make it very simple indeed.
So have you tried other benchmarks? For instance, if you take TPC-C, off the box it seems CryptDB can't run.
Yeah, good question.
Can't run any or very few.
Good question. So TPC-H analytics query, right? So TPC-H has a lot of summations, complex aggregates. Exactly. Whereas CryptDB is more like for OLTP type benchmark. That's like CryptDB's goal. So it wouldn't be fit for TPC-H. But actually, there's ongoing. There was work at MIT following up CryptDB that specifically looked at TPC-H and had clever database techniques such as splitting queries and maybe materializing certain queries, and they wrote really a smart query planner to figure out how to split dynamically, and they supported all of TPC-H, and the overhead was twice, at most less than twice. So basically, the overhead was less than twice in terms of throughput, and again, they had huge database size. They went to disk, so it was a purely database work.
I'm forgetting the database administrator. If you come to me and want some data about me, what promises can you give me about them not leaking out to the wrong people? And will they all be void the days of Boston and want some crazy statistics, and that forces the whole database to be exposed?
No, so I come and I tell you the following. I say, you have two choices. One, you compute on unencrypted data. You don't have anything. Or two, you use CryptDB. And basically, for fields that remain in rand, you leak nothing. And for that you could lick something, and for OP you could lick something else. Basically, there's the choice is nothing versus the security CryptDB provides. And I think it's worth it.
Did you look at the amount of data that actually gets transferred between the encrypted DB and the proxy DB as a comparison in the encrypted case versus the unencrypted case?
So we haven't measured that specifically, but that really is just so what gets transferred between the two query and query results. So the query contains encryptions of value, so it's slightly larger. And the results, we don't return any additional results besides the ones that are, we just return the actual results. CryptDB doesn't return a superset. So just the actual results, of course, they're a bit larger because they're encrypted. But no, we didn't look at the actual expansion factor. And I think that's because it's covered by other measurements. For example, it's covered by how large the storage becomes. That would give you an expansion, a sense of the expansion for the encrypted, for the results, but yeah.
For the OP sessions, you're doing multiple rounds of queries.
As I said, the OP is a different paper. For that paper, did we look at message sizes? I don't think we didn't, but we looked at expansion storage and we looked at ciphertext sizes. So you could reconstruct those maybe from the microbenchmarks. But it is an interesting, yeah.
A simple metric like throughput would actually matter, right? Because now if your proxy is doing multiple round trips, your database throughput would reduce. By database, I don't mean database server, I mean the application looking at the database would say proxy and database is one.
I agree it would matter for throughput, but we measure throughput. I showed you throughput, so.
But that was of the database server, right?
Yes.
The application would be looking at the database as database server plus proxy.
Yes, we have experiments for that as well. We actually took PHPBB and we looked at the throughput of the application itself, which includes everything, proxy, database, everything. And actually there the throughput was actually lost, was even less because of all the overhead of PHP, I think. So the throughput was something like 4%, 5%, but that's because the web applications are so slow that throughput was. But yeah, there we counted everything, including
I think that was the point that was being made, which is if you had unencrypted data, you don't have a proxy in picture at all. But now that you have the proxy and you might be doing multiple round trips, your overall throughput might reduce, ignoring current web applications that have PHP and maybe inefficient.
Right, I agree, but you can always have proxies in parallel, and I guess the database server, at least the way we look at it, the database server is the bottleneck because multiple applications share the database server, the same database server, whereas each application can have its own proxy, so it's not as important as the throughput of the database server. But I agree with you.
So maybe we'll stop here and take questions offline. Remaining questions?
I'll hang out. I'll be around. Thank you.